Ever sit in front of a blinking cursor, type a question, and watch an answer stream across the screen? It is startling how quickly that text appears. Behind that stream of text, the AI calculates every single word through complex math, live, the exact moment you hit enter. This live generation process is called inference, and running inference for millions of people at once is a lot like operating the kitchen of a frantic, high-end restaurant. Making sure those massive mathematical calculations happen fast and cheap without the kitchen catching fire requires an entirely separate, invisible discipline called inference engineering. Every time you ask an AI a question, the response happens in 2 steps. First is prefill. The AI comprehends your entire prompt all at once, like a head chef reading a long order ticket. Second is decode. The AI writes the response out one word at a time, like a chef tossing individual ingredients into a pan. These 2 steps require completely different resources. Reading the prompt during the prefill takes a massive, immediate burst of brain power, but writing the answer during the decode is slow and heavily relies on memory to remember the words it just wrote so the sentence makes sense. Trying to balance that heavy brain power with that slow, memory-intensive writing process is a massive bottleneck. If an engineer wants to serve thousands of users at once, they have to solve this puzzle. To cook these digital meals, the physical hardware you need is called a GPU, or graphics processing unit. You can think of GPUs as the expensive industrial ovens of our digital kitchen. There is a constant tug-of-war happening here. You can buy fast ovens to serve one user immediately, but that makes every response very expensive. Or you can pace the hardware to serve thousands of people at once, which brings the cost down. To maximize the oven's time, engineers use a trick called batching. Instead of cooking one meal entirely before starting the next, the AI weaves multiple user requests together. It's exactly like dropping 50 orders of fresh French fries into the deep fryer at the exact same time. They also use a trick called prefix caching. When people ask similar questions, the AI reuses the data from the prefill phase to skip doing the exact same math twice. It's like a prep cook making a giant batch of base sauce in the morning so it is ready to go for the dinner rush. By weaving orders together and prepping the common ingredients in advance, those expensive ovens never sit idle. The system can handle a massive volume of requests efficiently. Sometimes the model needs to move even faster. Engineers achieve this through a process called quantisation. This means lowering the mathematical precision of the AI. Instead of calculating a recipe down to 4 decimal points, it rounds to the nearest whole number. This rounding process does mean the AI loses a tiny bit of perfect accuracy, but it frees up so much memory that the response time drops. Then there's speculative decoding. The system uses spare computer power to draft the obvious next words in a sentence, acting like an incredibly smart autocomplete. It's like a sous chef quickly laying out the likely ingredients for a dish. Instead of generating the response from scratch, the main AI model, the master chef, acts purely as an approver. It glances at the drafted words and instantly validates them. Engineers can tune how strict this validation is depending on the task. If the AI is writing a medical document, the checking is rigorous. If it's writing a creative story, the rules are looser and faster. By shifting from writing out every single word to simply checking a drafted list, the AI bypasses the slowest part of the process, producing text at a speed no human can match. But what happens when a digital recipe is simply too large to fit inside a single GPU oven? When that happens, engineers use tensor parallelism. They slice a single massive calculation into fragments. Those pieces are then processed across multiple interconnected GPUs at the exact same time. They can also use expert parallelism. This routes specific types of user prompts to dedicated subsections of the model. A math question goes to the math section. A history question goes to history, bypassing unnecessary calculations. This coordination organizes a multi-station factory floor from a single overloaded processor, allowing it to handle the smartest models in the world. All these tricks work perfectly in one kitchen, but a viral app must handle millions asking questions at the exact same second. To handle the rush, the system uses autoscaling. It automatically detects spikes in traffic and turns on more GPUs to meet the demand. When things quiet down, it powers them off to save on cloud costs. Engineers also spread their operations across different providers, like Amazon and Google. This multi-cloud setup ensures that if one company has an outage, the entire AI system stays online. They also place physical servers close to the users. This speeds up the time it takes for the data to travel, while ensuring they follow local data privacy laws. When you string all these infrastructure pillars together, you have an engineering operation running on a planetary scale to maintain reliability 24 hours a day. Which brings us right back to where we started, that simple blinking cursor in your chat window. In the split second after you hit enter, your prompt is pre-filled, batched with other users, checked against drafted words, and routed across a global network of servers. While the model's intelligence provides the answer, this massive lightning-fast logistical engine makes the delivery to your screen possible.